I'm recording. Okay. Okay, before starting today's lecture, do you guys have any questions before starting? I guess not. I hope you guys started to implement your code, start your programming assignment as soon as possible. Many times I'm telling this one because that programming assignment, like if you try to do that in the last minute, probably you will not finish the programming assignment. And I mean, the second programming assignment will be kind of similar to this one, like the first programming assignment. It will be something like that. So don't think like, hey, okay, I will not do the first programming assignment. I can do the second one, third one, whatever. I suggest you to start learning the first parts because the second programming assignment will be quite similar. In second programming assignment, basically we will develop a multiplayer game. But when I say multiplayer game, don't be scared. I'm not expecting to develop some kind of huge games. It will be some network games, basically some kind of board games. We will see that when I assign the second programming assignment. It's gonna be fun, don't worry. But still, you need to learn how we do this network programming stuff, like socket programming, basically. Okay, time is 11 something, so we can start. So in our last lecture, we cover RDTs, like we started from the most basic one, most basic reliable data transfer, and then we are basically building up, and now last we covered RDT 2.1 when we had acknowledgement and negative acknowledgement. So like whenever you are the sender sends the packet. Let's say, let's do a quick recap because this is important. This is the sender, this is the receiver. Sender sends the packet. Receiver, if receiver receive the packet, if everything is good, this one sends acknowledgement and this is done. Sender sends a packet. If something goes wrong, let's say the packet is dropped or packet has some bit error, something is wrong. So the receiver sends negative acknowledgement. That means, hey, I didn't get the packet, so retransmit the packet one more time. If the retransmission works correctly, if I receive the packet in the retransmission phase, now I can send an acknowledgement. Assume that retransmission didn't work as well. So at this point, receiver will send negative acknowledgement again. So the sender needs to retransmit until it reaches to the receiver, until the sender receives an acknowledgement message. So this was the main idea of RDT 2.1. So let's move to, let's make it a little bit more complex. So RDT 2.2. A negative acknowledgement free protocol. So basically the idea is, instead of like the main idea is, so I don't need a negative acknowledgement from the receiver, right? Because the idea is, hey, if I don't receive acknowledgement, that means something went wrong. So I can assume that something went negative, so I can retransmit without waiting the negative acknowledgement. I'm just reducing the overhead, additional packet overhead. Like, because here, this is the sender, this is the receiver. Assume that I send the packet. I'm waiting an acknowledgement. I didn't receive an acknowledgement. So basically, at this point, I can send the packet, retransmit the packet again, and I can receive the acknowledgement. If I receive acknowledgement, I know everything is fine. If I don't receive anything, I know something is wrong. So This is why we don't need a negative acknowledgement. So, and also another stuff, a duplicate acknowledgement at the sender is the same idea of the negative acknowledgement. We will understand what is duplicate acknowledgement. I will explain that because let's see, do I have a slide for that? Okay, let's go back. So, for example, this is the sender, this is the receiver. This one sends the packet number 1, P1. I'm expecting acknowledgement number 1, but I didn't. If I assume that, so in TCP, we will see this one. Let's say you didn't wait and you sent a P2, the packet number 2. In return, if you receive, let's say, acknowledgement number 1, or acknowledgement, let's say, number 0, the previous one, that means the receiver didn't receive this one and didn't receive this one. So basically, you are getting a previous acknowledgement, like the last successful packet's acknowledgement. That means something is wrong, you need to retransmit. We will learn this one in details, don't worry. I know this is a little bit complicated right now, but we will learn in details in a couple of slides later. Let's move and understand, but I hope you understand the main idea why we don't need negative acknowledgement. That's the main thing. This is the finite state machine. Basically, the idea is if you don't receive acknowledgement until some point, basically retransmit the packet. That's the main idea. This is the receiver side. If you receive the packet, send acknowledgement. If you don't receive something, you don't need to send a acknowledgement, obviously. Or if the packet is corrupted, you will not send the acknowledgement for that specific packet. Okay, let's move to RDT 3.0. Let's make a little bit more complicated. Channels with errors and loss. So our assumption is now underlying channel, like our channel can also lose the packets, like the data packets and acknowledgement packets. So the packets can be dropped during the transmission phase. That means if the data loss, let's say the sender sending the packet, but the receiver doesn't even receive the packet. In some intermediate router drop the packet. So the receiver doesn't even know if the sender is trying to send the packet. Receiver has no idea. This is number one condition. Or sender send the packet and sender is now waiting an acknowledgement. Packet is received by the receiver. Sender is just waiting. And receiver assume that it sent an acknowledgement message, but the intermediate router, something happened and that acknowledgement packet is dropped. Now, sender is waiting the response from the receiver, and receiver just assume that, hey, I just sent the acknowledgement, I should be fine. But in reality, both of them has no idea. So that means we need additional stuff to check these conditions. So here, let me go back a little bit. So how can I solve this problem? What can I do? Any idea? Any guess? Do I have any guess? What can we do? How can we solve this problem?
Well, is that thing that I was talking about with the, I don't know.
So, okay, for example, assume this scenario. You tell me hi, I didn't tell you hi back. So what you do? Like, what is the you say hi back, right? Hi one more time, because you can assume that I didn't hear you. Obviously, you can assume that I hate you and I don't want to say hi, but in this case, you didn't do anything wrong to me, so I don't have any reason to hate you, right? So if you say hi, probably I will say hi back, so you know that. So what you do, you just wait my response a little bit, and if you don't hear my hi back, basically you will say hi one more time, right? So this is the main idea, this is the main scenario. So at this point, we can do the idea of timeout. We can use a timer. This is the solution for this one. So what is the idea? Sender sends the packet. If it doesn't receive an acknowledgement, it waits some time, because I mean, I send the packet, I say hi, maybe let's say I'm talking with someone, I'm busy, I couldn't reply right back because I have more important things to do. But at some point I can go back to you and, hey, that's it. I can say, okay, I hear you, and I give a response to you. This can happen. So you need to wait a little bit. But okay, you waited some time, and probably I didn't hear you, or maybe I say hi back to you, or you didn't hear me. Something went wrong. So you say hi one more time, and I say, oh, okay, I didn't hear you say hi, or you didn't hear me saying back hi. Doesn't matter. Something went wrong, and I don't mind to say hi one more time. And when I say hi, you hear me. So now the transfer, hi, hi, everything is done. You sent hi, I sent hi back, everything is perfectly fine. So this is the general idea. So the sender waits a reasonable amount of time for acknowledgement. Like, it starts a timer when it sends a packet, it waits, and if the sender doesn't receive an acknowledgement with a given that time frame, and then basically the sender sends another, like the same packet, retransmit the packet. Because we are using a sequence number, so for example, your packet is, let's think about this scenario. You send the packet number 1, the receiver acknowledgement dropped. So the receiver already received the packet, but you didn't receive the acknowledgement. So after the timeout, you decide, because you didn't receive the packet acknowledgement, you send the packet one more time, you retransmit. Now, if we don't use a sequence number, basically the receiver doesn't know if the packet is the same or a different, right? If we don't use a sequence number. But we are using a sequence number, so the receiver knows that it already has P1 data, the packet 1 data, because of the sequence number. So the receiver basically solves the duplication problem. So what the receiver now will send an acknowledgement 1 packet, and sender receives it. Okay, this is the main idea, why we are using sequence number to solve the duplication, why we are using timer, because of the acknowledgement packet can be dropped, or the packet itself can be dropped, because like in real life, these acknowledgement messages are also a packet, also data packet. So it can be dropped as well. It can something can happen to acknowledgement packets as well. So we need to take care of everything. So this is the finite state machine for RDT 3.0. As you can see, whenever we make some addition, it gets complicated. So this is the general idea. I will not go line by line, but as you can see, whenever we have timeouts, whenever we send the packet, we start a timer. Whenever timeout occurs, we send another packet one more time. And whenever everything is done, we stop the timer, and so on, basically. You can go and check this finite state machine in your free time. If you have a question, you can ask me. But this is a little bit complicated, so I will not go in full details. So RDT 3.0 in action. RDT 3.0 is very close to TCP, like the so we need to understand this one really good actually. So assume that the sender sends the packet 0 in, we are checking no loss case, like no error, no loss. So sender sends the packet 0, the receiver receives the packet 0, and the receiver sends an acknowledgement 0. And then basically the process goes like this. Sender sends the packet 1, receiver receive, and it sends the packet, and so on. Send the packet, receive acknowledgement, send the packet, receive the acknowledgement, and so on. In packet loss case, you send the packet, let's say you receive the acknowledgement, everything is fine. Assume that you send another packet and the packet is lost. And remember, still we are doing a stop and wait idea. We send the packet until we receive the acknowledgement. We don't send a new packet because of stop and wait idea. So sender send the packet, wait for an acknowledgement, but something happened. The packet is dropped, so you are waiting. You don't receive any acknowledgement. After some time, because whenever you send the packet, you start the timer. After some time, you basically, if you don't receive the acknowledgement, you resend the packet. And then assume that it is received. The packet is received at this point, and you receive acknowledgement. You can start sending a new packet. Assume that you have acknowledgement. This was the packet loss case. Assume that you have acknowledgement loss. You send the packet here. Okay. Here it is obvious. You send the packet, the receiver received it, sends an acknowledgement, nothing to worry. But whenever the sender sends another packet, assume that the packet arrived by the receiver and receiver sends an acknowledgement for the packet. But the acknowledgement is lost before arriving to the sender. So now sender has no idea if the receiver received the packet or not because it didn't get the acknowledgement. So the idea is it waits the acknowledgement. If it doesn't receive the acknowledgement after the timeout, it will resend the packet. And basically, because of the sequence number, like packet number 1, the receiver will detect the duplication. So basically, nothing to worry because of the sequence number. And sender basically sends an acknowledgement, and life is good again. Premature timeout or delayed acknowledgement, this can happen as well because like you cannot set the perfect timeout, a perfect timer, because of the network congestion. Not all timeout can be the same. It depends on the round trip time. It depends on lots of different things. So this premature timeout can happen. So the idea of the premature timeout is here. Let's assume that you send the packet and receiver receive the packet and sends an acknowledgement. But during this acknowledgement time, assume that something went wrong and like maybe a network congestion, maybe something happened during that packet creation time, whatever, not important. You had a timeout. You didn't receive the acknowledgement. So you need to resend the packet as a sender because you didn't receive an acknowledgement. So here you resend the packet, and basically because of the sequence number, the receiver detected duplication. So it say, okay, something went wrong. Probably it didn't get my acknowledgement. I will assume that whenever I detect a duplication, I will assume that something went wrong, and I will send the last successful acknowledgement. This was, as you can see, this was my last successful acknowledgement. So I send the last successful acknowledgement. Here you receive a double acknowledgement because it was a delay acknowledgement case. So basically, okay, packets are arrived now. I can send a new packet. This is the main idea. So this one shows performance of RDT 3.0, some mathematics involved. Let's see. RDT 3.0 is basically, it works perfectly fine. I mean, if you put RDT 3.0 in the internet, as an reliable data transfer, it works. But the main problem is because of the stop and wait idea, because the performance is so bad. Just imagine, you send the packet and you are waiting some time until you receive an acknowledgement, like you are wasting lots of time. So this is the mathematics behind, okay, the transmission delay is the bit divided by R, the speed, basically like the rate. If you are trying to send like 8,000 bits, and if you are using 1 gigabit per second link, basically it takes 8 microseconds. If you can check the utilization of the sender is 0.00027. So like you are using 1 gigabit per second link, but the throughput, actually you are using 33 kilobyte per second. It is like crazy. So basically you are wasting lots of your resource, and that's why the utilization is terrible. The performance is terrible. So we cannot use this protocol, this scheme in the real internet. Because just imagine, like even with the perfect link, you will waste all your resources, and it is no brainer. You need to improve this utilization. You need to improve your performance. Otherwise, this cannot be applicable to the internet. So this is the main problem of the stop and wait, because here, this is the sender side, this is the receiver side. Sender sends a packet here. The packet, the transmission is L divided by R. L is the packet size, R is the rate. So this is the transmission time, the trans. Because of the stop and wait, you need to wait RTT, round trip time. Round trip time means you send the packet, you receive the response. This is round trip, RTT. This is half of, basically, this is not RTT. This is plus, this is RTT, round trip time. So that's why you are waiting RTT time and you do nothing. So this is waste of resource. What can we do? How can we solve this problem? Any idea?
Obviously, do something while you're while you're waiting. Maybe send another packet.
Exactly. Why I'm waiting this one? I'm just waiting and I do nothing. Instead of waiting, this is packet number 1. I can send packet number 2, packet number 3, packet number 4, whatever. And basically, whenever the receiver receives that packets, it doesn't have to wait another time. It can send acknowledgement like this. So if I don't receive the previous packet's acknowledgement, I can retransmit that packet. So I can utilize this link as much as possible. So this is why we are using multiple packets at a time, because of we are trying to improve the utilization. This utilization is no brainer because you are wasting this time slot, huge time slot. Okay, that's why we are using pipeline protocols. Pipeline means send multiple packets and then basically receive multiple acknowledgement. That's fine, I don't care. But whenever I receive some bad acknowledgement, let me say, okay, I sent packet number 2, but I didn't receive the packet number 2's acknowledgement. So the idea is, if I don't receive the packet number 2's acknowledgement, that means something went wrong. So I can send that packet again. Yes, I'm adding additional complexity to my system, but I'm improving the performance and efficiency a lot. So this is stop and wait. You send the packet, you are waiting until you receive the acknowledgement. This is pipeline version. You send multiple data packets and you are receiving multiple acknowledgement and so on. Obviously, we need to use some buffer at sender and the receiver because we are using multiple packets. We need to keep record because remember, TCP provides in order delivery. So all the packets needs to be order. So you cannot send packet number 2 before packet number 1. You need to send packet number 1 and you need to make sure that the receiver received packet number 1 perfectly fine. After that, it can put P2 in the sequence order because of in order delivery. Okay, that's another important thing because now you are sending multiple packets. You are not sending only one packet. So the sequence number cannot be binary anymore. Remember, RDT 2.0, I believe we put a sequence number part. The sequence number was binary, 0, 1. If the packet is received or not received, that's it. We have only one case. But now you are creating multiple packets and each packet can be received or not received. So, and each packet needs a unique sequence number. Otherwise, it can overlap and basically you cannot handle duplication. The server needs to override some packets, which is basically crazy. It cannot happen. So the sequence number needs to be more than binary. We have 2 generic forms of pipeline protocol. These are extremely important. Go back and selective repeat. We have 2 pipeline protocols. And in TCP, like in real life, we are using pipeline. Obviously, we are not using a stop and wait because of the efficiency and utilization. Okay, assume that we are using, instead of 1 packet stop and wait, assume that we are using 3 packets at a time. Not 1, we are sending 3 packets and we are receiving 3 acknowledgement, that kind of stuff. We don't wait for the first acknowledgement and we are just sending the 3 one. As you can see, every ID is the same, but because of the 3 packets idea, you improve the utilization by the factor of 3. Obviously, in real life, even 3 is like Even we are increasing the packet size. This is just a simple example. We are increasing the packet number a lot, not even 3. We will cover that, don't worry. We will see in a bit. Let me see, should I explain more stuff here? Okay, let's try to understand go back and selective repeat. These are very important concepts. So go back and the idea is sender can have up to an acknowledgement packet in the pipeline. N is basically the number you are predefined. For example, you are sending, I will send 5 packets at a time. For example, in here, our N is 3. That means I will send 3 packets at a given time, and I need to receive 3 acknowledgements. If I don't receive 3 acknowledgements, basically, I need to think something went wrong, so I can retransmit that packet number. So, receiver in go back and receiver only sends cumulative acknowledgement. Cumulative acknowledgement means last successful packets acknowledgement. It doesn't act like if there's a gap. Basically, you send the packets, several packets, P1, P2, P3. Okay, whenever this one receives P1, it sends the acknowledgement. Obviously, it sends the acknowledgement, it sends the acknowledgement. Okay, this is the general case. Assume that something happened and you didn't receive P2. But you receive P3. You receive P1 and you receive P3. Just a second, sorry about that. So, whenever you receive P1, oh, sorry. Whenever you receive P1, basically you will send P1's acknowledgement, acknowledgement 1. Here, you didn't receive P2. So basically you didn't know, you didn't receive anything. If you didn't receive anything, you don't reply anything. But whenever you receive P3, you didn't receive P2 yet. So here, you will send acknowledgement 1 more time. You will send last successful acknowledgement, last successful packet delivered in order. You receive P3, but you didn't receive in order. So that's why my last successful packet arrived in the order was packet number 1. I resend the acknowledgement number 1 at this point. So obviously we are still using the timer when we introduce RDT 3.0. At some point, when you receive the timer, timeout, at this point, basically, because the sender didn't receive acknowledgement packet number 2, this will send P2, this will send P3, and so on. Go back and that means even P3 is delivered because it is not order, the server drops that packet. You need to send in order. We will cover this part a little bit in more details. Don't worry. This is the generic idea. In selective repeat, the idea is instead of using cumulative like this, basically use a buffer in the sender receiver side. Whenever you receive something in good, basically receive like P1, you didn't receive P2, put it in P3. So the sender can only retransmit P2. instead of P2 plus P3. So whenever the time's out, the sender only sends an acknowledgement packet. So each packet is individually acknowledged instead of a cumulative acknowledgement. Okay, this is the overview. We have time, so we can go in details because this is very important. Let's try to understand go back and idea. So this is the sender side. So we have, let's say, some k-bit sequence in the packet headers. So we have some packet size. We will send several packets and assume that our window size is n. So we can send n packets given a time. So we started from the beginning. Receiver received, send an acknowledgement. Receiver received, send an acknowledgement, and so on. Whenever sender received an acknowledgement, it slides the window to the next part. So whenever it slides the window, basically it will send the next packets. Whenever the receiver receives, it will send the acknowledgement. Let's see it in an example. This is finite state machine. This is self-study. I will not cover. You can check in your own time. I will solve it in an example. Okay, go back and in action. This is extremely important part. Assume that you have 8 packets. You need to send total number of 8 packets. And assume that the number n is 4. Let me take it. Number n is 4. That means you can send 4 packets at a given time, at most, because of the window size. This is your window size. So first, your windows start from the beginning. 0, 1, 2, 3. You send packet number 0, 1, 2, 3. So now you are waiting acknowledgement because like you send bam, 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 4 packets at a given time. You are waiting acknowledgement because of your window size is n. You send all the packets. Assume that the packet 0, packet 1 arrived. The receiver arrived at packets, it received. So whenever the receiver received the packet, it sends the acknowledgement. Here, it sends the acknowledgement. It sends the acknowledgement. Whenever the sender receives an acknowledgement, it slides the window. Here, sender received the acknowledgement 0. That means packet 0 is arrived by the receiver. Everything is perfect. I don't need to send packet 0 anymore. Packet 0 is done. I'm sliding my window. So now 1, 2, 3 is already sent. I didn't send packet number 4 yet. I'm sending packet number 4 here. You received another acknowledgement, packet acknowledgement 1. It means the packet 1 is everything is fine. You don't need to send packet number 1 anymore. This is sent, this is sent. You slide at your window. Packet number 5, you can send packet number 5. Okay, the trick part starts here. You sent packet number 2, but something happened that packet and the receiver didn't receive the packet 2. So it didn't send an acknowledgement. You also sent packet number 3 and the receiver received the packet number 3. Because it didn't receive packet number 2, the sender basically discard, like to drop the packet because it is not in the order. It will send last successful acknowledgement. The last successful acknowledgement was acknowledgement number 1. So the sender sends acknowledgement 1, last successful acknowledgement here. Clear? So here, this is the last successful acknowledgement. Because the sender already received acknowledgement 1. So the acknowledgement is duplicated. So basically, hey, something is wrong. I already sent that packet and I received the same acknowledgement. So some packet loss happened. So what happens? Here, you send packet 4 and packet 5 when you receive X0 and X1, remember? But because of packet 2, drop of packet 2, you discard the packet, you are sending the last successful acknowledgement. So, as you can see, the sliding window remain the same during the duplication of acknowledgement because the receiver didn't receive packet number 2, 3, 4, 5. Yes, it received packet number 3, 4, 5, but it dropped the packet because it didn't receive packet number 2. So what happens? We wait until the timeout. And whenever timeout happens, the sender starts the process from the beginning. It will send all the packets in the window 2, 3, 4, 5. And then basically receiver sends an acknowledgement in the given time. Let me just check something. Let's see. I want to show you how go back and works in a let's see. So this is just you can access, like you can just type Google like go back and selective repeat in Google. You will see how the algorithm works basically. Let me make it a little quick. So assume that this is go back and this is the window size is 5. Let's start. For example, here you send 5 packets and the receiver received the packets, received it. Whenever received, as you can see, the window is sliding. Okay, assume that this packet is lost. Received, move. Received, move. As you can see, this packet is not received. So this one sends acknowledgement of the last successful one. Here. Timeout happened here. Now I'm sending all packets in my window. I receive the acknowledgements. So I'm sending the packets. Assume that this packet is dropped again. Here, last successful packets, as you can see here. And now the timeout occurs. I'm sending all the packets. Okay, assume that this acknowledgement dropped. Here, let me stop this. Why this one? Let's see. I hope you guys catch the previous one. Didn't I stop already? In the previous one, this one sent, this one sent, and sent. As you like, this one receive, but the acknowledgement packet of this one was dropped, but the acknowledgement, these guys arrived correctly. Even though I lost this acknowledgement, I slided my window. Why is that? Any idea? Any guess? Let me show one more time.
The sender, I guess the mechanism, understands that the packets are received in order. So if it received, packet 8, then it knows that packet 7 was received, but the acknowledgement just wasn't sent. I don't know.
Exactly. That's the main idea. That is why we are doing so. Because of the cumulative acknowledgement here, assume that this one is lost, but now this one sends a cumulative acknowledgement. Here. So it sends a cumulative acknowledgement of the last successful packet arrived. So assume that this is the last successful packet arrived because of the sending acknowledgement. Let's say you don't even you don't get the acknowledgement for these previous items. You know that because of this cumulative acknowledgement, you know that these previous packets are already arrived. So life is perfect. Everything is good. You don't need to worry about it. Good. This is how Go backend works. I will not cover, I will stop here. I will explain selective repeat in our next lecture because we don't have time. But this is the general idea of Go backend. So if you have a question in Go backend, you can ask me now.
So does it, I know when the sender times out, the illustration shows like all of the window packets sending at the same time. Obviously, like in reality, are they sent kind of one after the other?
What do you mean by?
Oh, I mean, if you just let this illustration, if you just let the sender time out, you'll see that like it's not like, firing off packets one after the other. It just sends all 5.
Because of this simulation, in reality, obviously, you don't send exactly the same time. You cannot, because it will take L divided by R, as we covered that each packet is some transmission delay. So each packet will take some small L divided by R delays. This is just a simulation environment problem. In real life, obviously, the packets are not delivered at the same time. It is impossible.
I just wanted to clear it up. Thank you. That's what I thought.
This is because of this website. They just want to do that in that way. In reality, the packets, whenever this one goes like this and so on. It cannot be at the same time in reality. But anyway. Sure.
I had a question too about the difference from how you were showing a cumulative delay, how it automatically went back to, it still shift the window over. How you were saying the cumulative delay? What's the difference between that and when it time out and automatically starts to send it? What's the two differences?
So whenever the timeout occurs, you basically send your entire window. So here right now, this is your window, right? Window is 5. All the previous packets are already arrived. So let's say timeout occurs. At this point, whenever timeout occurs, you start the process from the beginning. You basically assume that, okay, now I'm starting from this one, start the process from the beginning. You don't need to worry about what happened in the previous one. You start sending with the current window, and then the process is exactly the same. Send everything. Whenever you receive, slide the window. Whenever you receive, slide the window. If you don't receive, stay in the window. So whenever timeout occurs, send entire window again. Start the process from the beginning. That's the main idea. Timeout means reset. Reset the process and start from the beginning.
And the other one, the cumulative one, it just keeps going as it goes. It just resets it as it goes.
Yes, whenever the sender receives a packet, it will always send last successful acknowledgement. Assume that if the receiver doesn't get this packet, but it gets the packets of the remaining one, it will always send this acknowledgement because this is the last successful packet arrived. But whenever the sender receives this packet, let's say, The packet is arrived. So now this is the last successful acknowledgement. It will send this acknowledgement. The last successful acknowledgement. The sender always sends the last successful acknowledgement. This is the cumulative idea. Assume that this one received, and this one is not received, but these two are received. So this is the last successful acknowledgement, right? Because you didn't get this one yet. Even though you get this one and this one, but you didn't get this one. So the order is not correct. You send the last successful one as an acknowledgement.
Yeah, it really just benefits the sender, you know, like the sender knows that it receives the last successful acknowledgement. So therefore, if it doesn't receive an acknowledgement for the previous packets, it still knows that they were received.
Exactly. That's the main idea. That's the good part of this one. This is less complicated. It is when we learn selective repeat, you will see that like in the next class, it will be a little bit more complicated than the go back and so we will cover that in Friday lecture. Questions? I strongly suggest you to like just check this website, or there are like several different websites like this kind of simulation. Try to understand what is the go back and algorithm, because in homework and in your test, you will get a question from go back and selective repeat. So try to understand these two protocols. These are important.
Did you assign a date for the midterm?
At the end of this chapter, we will have our midterm. Probably it will be something in 2 weeks, before mid-October, something like that. We will have our midterm.
And the assignment is due on the 14th. Is that what you said? That's what I got on my calendar.
I am not sure. I'm not sure about the deadline of the programming assignment. I don't remember. Probably something like that.
Okay.
Mid-October, yeah, probably it's right.
All right. Thank you.
Okay. Okay, so bye everyone. See you on Friday. We will cover selective repeat on Friday.
All right.
Bye.
Adios.